Hello everyone, welcome back to my channel. So in this video we are going to learn about another type of ADC, which is dual slope ADC. Okay, so dual slope ADC, and this shows the circuit diagram of dual slope ADC. Okay, so first of all we will learn the operation of each and every component which is used here, and then we will do analysis, and then we will derive the equations required and important points that to be remembered. Okay, so we'll follow this sequence only. So in dual slope ADC, first of all you have two inputs, VA and VR. Okay, so VA is your analog input voltage and VR is your, suppose I'm taking it as a reference, so V reference is your reference voltage. Okay, so the condition here is VA and V reference must be opposite in polarity. Okay, so which are opposite in polarity? The input voltage and reference voltage must be opposite in polarity. So I'm taking VA as negative and V reference as positive. Okay, so you can take any way. Okay, so I'm taking like this, right? So this is about VA and V reference. Okay, so the next part here is this one. This is, so here the positive terminal is going to be grounded. So this is integrator circuit. Okay, this is integrator circuit using op amp. So it is in inverting configuration because non-inverting terminal is grounded. Yes or no? So non-inverting terminal is grounded, so it is in inverting configuration. So since it is in inverting configuration, so what will be the output of integrator? So V0, I am taking this as V0. So V0 is equal to integrator output I am taking. Okay, so whatever may be the input. So here you are using a switch here. Okay, here you are using a switch here. Okay, so integrator output, the input may be either VA or V reference depending on this value of T. I will tell you now. Okay, so V0 is equal to minus 1 by RC integral V in. I am taking it as V in into dt. This V in may be either VA or maybe V reference. Okay, so this depending on time. Okay, we'll discuss that later. So this is the integrator circuit and this is the operation of integrator, and this will be the output equation. This minus because it is in inverting configuration. Okay, and again this is a comparator circuit. Okay, so this is one comparator circuit. So output of this may be either positive, output of integrator may be either positive or negative. If it is positive, then output of comparator is 1. If this value is negative, then output of comparator is 0. Okay, so this is the comparator operation. So output of comparator depends on the negative or positive voltage from the integrator, and the integrator will depends on this VA or V reference value. Okay, so depending on the comparator output, it is given to clocked AND gate as we have discussed. Okay, so this is clocked AND gate because clock input is given to yes. Okay, so this is clock input, right? So when the output of this comparator is positive, then 1 will be obtained at the output of this comparator. Then clock pulses are passed through this AND gate. If the output of comparator is 0, then no clock pulses will be passed through the AND gate. Okay, so this operation we have already seen, right? So if the output of AND gate is 1, then clock pulses will be transferred to binary counter. If the output of this comparator is 0, then no clock pulses will be transferred to this binary counter. Okay, so this is the operation of clocked AND gate. right? So next is binary counter. So this is generally binary up counter. So counter, depending on the clock pulses arrived, it will increments its value. Okay, so that is the simple operation of any counter. So MSB bit of this counter is connected to T flip-flop output. So generally this is a control circuitry. So this is a control circuitry which is used to control switch between VA and V reference. Okay, so VA and V reference. Okay, so always this will be in toggle mode because T is equal to 1. Since T is equal to 1, always T flip-flop is in toggle mode. Toggle mode means it will switches its value. Okay, so it will switches its value once your clocked pulse is high. Once your clock pulse is high, then it will switches its value. Right. So next, this is given as this is used to control the switch. Okay, so this is used to control the switch. So basically it is a control circuitry which is used to control the switch between VA and V reference. Okay, so these are the important, or these are the elements present in dual slope ADC. I'll just revise it. So there are two inputs, VA and V reference. VA is negative I am taking, V reference is positive, but the condition is they should be opposite in polarity. Okay, next an inverting configuration integrator circuit is used, which is used to charge or discharge the capacitor based on the input. So output of this integrator may be either positive or negative based on negative or positive inputs. Okay, so that if it is positive, then output of comparator will be 1. If it is negative, output of comparator is 0. So based on 1 and 0 from the comparator, the clock pulses will be given to binary counter. Okay, so then binary counter will produces the digital output. Okay, and then only when it is static, that means no clock pulses are applied. When no clock pulses are applied here, then only it will produce the static digital output. Okay, so until then this feedback mechanism will continues. Okay, so this is basically, this T flip-flop is basically a control circuitry which is used to control the switch between VA and V reference. Okay, so these are the important components of dual slope ADC circuit. Okay, so let us now do the analysis part. Let me take one more slide. I'll do the analysis part. Okay, so now let us see the analysis part of this dual slope ADC. Okay, so in the analysis part, first of all, what will happen? Suppose I am taking it as case 1. Okay, so parallelly I'll draw the waveform also. Okay, so for output voltage V0. Right, so in the case 1, what will happen is the first that means first initially VA is connected. Okay, VA is connected, which is negative. Okay, try to understand. Okay, bit complex, but try to understand. So VA is connected, which is negative. So since VA is connected, so what is V0 value? V0 is equal to minus 1 by RC integral some 0 to T1. We'll take T1 VA into dt. That means up to time T1, this VA is connected to integrator. Okay, so V0 is equal to minus 1 by RC VA into T1. Okay, since VA is negative, so minus into this negative minus becomes positive, so V0 is positive. Yes or no? V0 is positive. So V0 is positive, which is applied to comparator circuit. So V0 is positive, which is applied to comparator circuit, right? So V0 is positive, applied to comparator circuit. So output of comparator is equal to 1. So output of comparator is equal to 1. Then what will happen? Clock pulses will be transferred to counter. So clock pulses will be transferred to counter. So counter increments its value. So during this process, since V0 is positive, so the capacitor starts charging. So it starts charging like this. So V0 now becomes V0 now becomes a positive slope, right? So it increments its value. Therefore, what will happen? So when binary counter increments its value, the same value and then its value. So next, if you increase VA, then what will happen? Count value also increases. The same process will happen here. So this total process will happen. Then count value also increases and capacitor charges further. Capacitor still charges. So it will still charge to a high value. Okay, so if you go on increasing the value of VA, based on the value of VA, the capacitor charging increases. So this capacitor charging continues up to T1, that is maximum time. T1 is maximum time for charging, right? So T1 is the maximum time of charging. So until then capacitor charges. So maximum value which you can given is 2n-1. So maximum input voltage which you can give is 2n-1 for n-bit ADC. So now after 2n-1 clock pulse, so if your count is 2n-1, so 2n-1 clock pulses will already be obtained. Yes or no? So if your count is 1, then 1 clock pulse will be given to counter. So for obtaining the maximum value which is 2n-1, we require 2n-1 clock cycles. This we have already seen in each and every DAC. Okay. So after this what will happen? Counter resets. So after 2n-1 clock cycles, counter will resets. So when counter resets, then control circuitry, then what will happen? Control circuitry changes the input to V reference. Control circuitry switches the input to integrator circuit, switches the input of integrator circuit to V reference. Okay, so this happens for one more clock cycle because it has to reset, and that resetted circle is given here. So 1 into T clock, so one more clock cycle is required. So up to here the counter does not reset. So in order to reset the counter and give the next input, so it require 1 clock cycle. So total time required for charging the capacitor is 2 power n into T clock, the addition of these two. So T1 is equal to 2 power n into T clock. This is the time required for the capacitor to charge to the maximum value. And then afterwards what will happen? So now the control circuitry switches to V reference. So then what will be V0? V0 is equal to -1 by RC into V reference into, suppose it will be T2. Okay, since V reference is positive, this is a negative value. So V0 is negative. When V0 is negative, then no clock pulses will be applied. Okay, so no clock pulses will be applied. Yes or no? So no clock pulses will be applied and counter will be in that state only. Okay, so counter will be in that state only. Okay, so until it charges to this, and then what will happen when the output is negative? When the output is negative, capacitor starts discharging. So it discharges up to this value. Let this be T2. Okay, so during discharging time, this is the output equation. Okay, so the slope here is minus V reference by RC. This will be minus VA by RC. Okay, right. So this is the analysis of this. So when no clock pulses is obtained, then you can obtain the static digital output at the output of your ADC circuit. Okay, since if you see here, the capacitor charges up to T1 and discharges up to T2, you have two slopes here. This is slope 1, which is VA by RC. This is slope 2, which is minus V reference by RC. So that is why this type of integrate ADC circuit is called as dual slope ADC. That is why it is called as dual slope ADC. Okay, so let me explain you one more time because it is quite complex. So first, when VA is connected, then V0 is equal to this. Okay, so when V0 is equal to this, since VA is negative, as I have taken VA is negative, then VA is negative, so V0 is positive. When V0 is positive, then capacitor starts charging, so it charges to some certain value, right? So depending on the magnitude of VA, it charges to certain amount. Okay, so this is the maximum value I have taken, but if your VA value is less than the maximum, it charges to only finite amount and then starts discharging. So discharging time constant will be more. Okay, so this depends on the input magnitude, that is the conversion rate depends on the input magnitude in the case of flash type ADC. Okay, this is one of the important point which you have to remember. So when V0 is positive, then output of comparator V0 is positive, then output of comparator is going to be 1, and then clock pulses will be applied and counter increments its value. Okay, so and capacitor starts charging, right? So the counter counts up to the maximum value. Maximum value is 2 power n minus 1, so it will take 2 power n minus 1 into t clock. This is the conversion rate. Yes or no? So this is the maximum conversion rate, and then after one clock cycle, that is applying one more reset value, that is 0 0 0 0 to T flip-flop, MSB is connected, so 0 is connected to negative flip-flop, thereby this control circuitry will be activated. So control circuitry will be activated, which makes the input switching to V reference. When input switches to V reference, since V reference is positive, then V0 becomes negative. When V0 becomes negative, no clock pulses will be applied and corresponding digital output, static digital output will be obtained at the output of your, when no clock pulses are applied, then counter stops counting and that will be your digital corresponding output. Okay, so this is what it is happening in the case of dual slope ADC. Why it is called dual slope ADC means, so you have charging and discharging of capacitor. During charging you have one slope and during discharging you have another slope. That is why it is called as dual slope ADC. Okay, so now we will see the calculation of the time t2. Okay, so we know that the total output voltage is given by minus 1 by RC into VA into T1. So up to T1 it is minus 1 by RC into VA, and from T1 to T2 it is minus 1 by RC into V reference into, it will be T2 minus T1 for only certain period of time. So I'll redraw that. So this is T1 and this is T2. Okay, so within this time interval T2 minus T1, the reference is here, the slope is V reference by RC minus V reference by RC. Okay, so multiplied by time will gives you the output. So here time is T2 minus T1. So if you multiply by T2 minus T1, it will be the output in this part. right? So output in this part is the slope here is VA minus VA by RC into T1. So 0 to T1 is the time here, right? So total time is T1 minus 0, which is equal to T1. So this is the, so at T2, if you want to find T2, at T2 the output is going to be 0. So V0 is equal to 0 at T is equal to T2. So when you substitute V0 is equal to 0, what will happen? Minus 1 by RC into VA into T1. Okay, so directly I have actually have to take T minus T1, but I have substituted directly with the T2, so that is why I am taking directly V0 is equal to 0. Okay, so both ways you can write, is equal to 1 by RC into V reference into T2 minus T1. Okay, so minus 1 by RC gets cancelled off. So what you will be left over is minus VA by V reference into T1 plus T1 is equal to T2. So T2 is equal to, so in order to avoid this, I'll take a minus because VA is negative, both are opposite signs, so totally this term will be positive term only. So in order to avoid this, I'm taking a modulus over sign here, VA by V reference plus 1 into T1. Okay, so this is the time required for conversion, T2. Okay, so this is the value of T2. So total time required for conversion is T2. Okay, time required for conversion. Right, so this is then. So time required for conversion, if you observe here, it depends on input magnitude. Yes or no? So here, if you have more input magnitude, it will take more time to convert. Yes or no? Directly proportional. So if you have your input magnitude high, then it will take more time for conversion from analog input to digital data output. Okay, so that is the main disadvantage here, right? So this is value of T2. So what is maximum conversion time? So when will be the conversion time maximum? Okay, so when will be the conversion time maximum? When VA, so when charging of capacitor is equal to the discharging of capacitor, then we can have maximum conversion. So that means T2 is also equal to T1. This is T1 from 0 to T1, and after another T1, if you have the same value, charging and discharging have same value, then we can say that it is the maximum conversion time. It is the maximum time required for conversion, because when charging and discharging are same, then you will have maximum conversion time. When you have unequal values, then you will have conversion rate lesser when compared to this case. This will have the lesser conversion time always. Okay, so always maximum conversion time occurs when VA is equal to V reference. When VA is equal to V reference, if both are same in magnitude, then what will happen? T2 is equal to, so if you substitute in this, okay, so if you substitute in this, where T2 is the maximum time, right? So T max is equal to, or T2 or T max is equal, when you substitute this, what will happen? So both are equal, so you'll get 1 here, 1 plus 1 is 2, so you'll get 2T1. So what is the T1? T1 we have got it as 2 power n into T clock. So T maximum is equal to 2 into 2 power n into T clock, which is equal to 2 power n plus 1 into T clock. Okay, so this is the maximum conversion time in the case of dual slope ADC. Okay, so this is the maximum conversion time. Very important formula. Okay, so this is how, based on charging of capacitor and the charging and discharging of capacitor, you'll have the values of T2, and based on this value of T2 you'll have the conversion time like this. Okay, so the disadvantage here is how its conversion time is more, very high conversion time, very high conversion time, so operation is very slow. Okay, so operation is very slow in the case of dual slope ADC. So this is the disadvantage of this ADC circuit, but the advantage is it is very accurate. It is very accurate and used in DVMs, digital voltmeters. Okay, so this dual slope ADC is used in the construction of DVMs. Okay, because here one more advantage is no DAC is required, so we don't have used any DAC circuit in this, so no DAC is required, and hence it is cheaper. It is cheaper. So this is also one of the reason why we will use in commercial DVMs. Okay, so no DAC is required and hence it is cheaper, and also it gives very accurate result. Okay, so these are the important points, and this is how we can perform the analysis of dual slope ADC. Okay.